Hello everybody. In this video clip I want to quickly discuss with you the rate order of a Michaelis Menten enzyme because that is something really interesting. When we look at rate orders, of course we know that a rate order is just simply a mathematical concept that allows us to formulate a sort of a rate equation, and yet with the Michaelis Menten equation for an enzyme, we will see that our current concepts of rate orders, where everything is nice and tidy and everything is constant, sort of, this concept does not hold true for a Michaelis Menten enzyme. So let's write down the Michaelis Menten equation. B equals Vmax times the substrate concentration divided by Km, the Michaelis constant, plus the substrate concentration. And this is really our starting point. That is the famous Michaelis Menten equation. And if we plot that, when we plot, for example, the rate versus the substrate concentration, for a normal Michaelis Menten enzyme, we would get a curve like that. And what we see is that, contrary to what we have dealt so far with in terms of rate orders, it looks like that the rate order is changing and depending on the substrate concentration. So as a reminder, if we, for example, have a zero order reaction, we would find that the rate is totally independent of the substrate concentration. So that would be a zero order. If we had a first order reaction, we would find that there was a strict linear correlation between substrate concentration and the rate. And it seems that the Michaelis Menten enzyme does some very strange things. So let's see how we can deal with that. So the first case, let's say that our substrate concentration is very, very large compared to Km. So let's say, for example, the substrate concentration is 10 times Km. And we can calculate what our rate then would be if we just simply put 10 times Km instead of S in our Michaelis Menten equation. We would have V equals Vmax times S. So I write 10 times Km divided by Km plus 10 times Km. So that would give me Vmax times 10 times Km divided by 1 Km plus 10 Km gives me 11 Km. And we see that Km cancels out. And I have 10 over 11 times Vmax in this case, or that would be roughly 91% Vmax. So at high substrate concentrations, we are running close to Vmax. Now, what changes? Well, we can actually write Km plus S is probably fairly close to S. And we see that here we had S is 10 times Km, and here Km plus S gives us 11 Km, so it's close to S. So what do we get if we do this substitution? We have V equals Vmax times S, so that doesn't change. But Km plus S, this one here, we can just simply substitute with close to S. We see that the S cancels out, so we have V equals Vmax. And if we assume that Vmax is under given conditions is a constant, then all we have is V is a constant. Or we can, if we want to, we can write this also as S to the power of 0, because anything to the power of 0 is 1. So under these conditions, when S is really, really large compared to Km, we have a 0 order. Now what happens if we are very small with S? So S is much, much smaller than Km. So for example, S is 1/10 of Km. Let's go for that. We can, of course, we can calculate what our rate is. We just simply put 1/10 of Km into our Michaelis Menten equation, and we have V equals Vmax times 0.1 Km divided by Km plus 0.1 Km. Just substitute S. So I can put that together. Vmax times 0.1 Km divided by 1 Km plus 0.1 Km. That gives me 1.1 Km. I can cancel Km, and I get roughly 9% of Vmax. And if S is so much smaller, then I can write Km plus S is very close to just simply Km. So if I put that now in our Michaelis Menten equation, I get V equals Vmax times S over Km plus S, and instead of Km plus S, I just simply write Km. And I can write this also in a slightly different format. I can write this as Vmax over Km times S to the power of 1. And I can treat this here as a sort of first order reaction constant, first order constant. And I see that the reaction is a first order reaction. So basically, if the substrate concentration is very small compared to Km, we have a first order reaction. If the substrate concentration is very large compared to Km, we have a zero order reaction. And that is exactly what we see here with our Michaelis Menten plot. So here, right at the beginning, when the substrate concentration is very small, we have a first order. And this then changes when the substrate concentration gets very high into a zero order reaction. And in between, we have anything between this first order and the zero order. So a Michaelis Menten reaction can be anything between zero order and the first order reaction. And actually it varies with the substrate concentration. And one can show that actually the order of a Michaelis Menten reaction can be expressed as Km over Km plus S. And what we see is that the order actually depends on the substrate concentration. And that's something that we haven't had before. So I hope this makes sense, and thank you very much for watching.